very much. First of all, let me thank the organizers for the invitation. It's very nice to be back in Mainz. I'm going to tell you about boundary obstructed topological phases, which is a concept that we just put out in a preprint with Aslan Khalaf, Vladimir Benalcazar, and Taylor Hughes. And hopefully I'll get also to hint a little bit on another work, which is partial lattice defects in higher order topological insulators, which also can be used in order to see boundary obstructions. So let's go back to 2008, where topological phases were all protected by internal symmetries. That was, time reversal, particle Bow, and chiral symmetry. There was a very nice one-to-one correspondence between different few concepts. There was a bulk gap closing that indicated that you were going through a topological phase transition. There was protected boundary modes that were robust to perturbations that preserved the symmetry, and maybe a little bit less appreciated, there was no way to construct atomic orbitals which are symmetric and fully localized, exponentially localized in real space. There's a nice one-to-one correspondence between all of these concepts. Nowadays, we have crystalline symmetries, and these correspondence become way more subtle. For example, you can have bulk gap closing transitions between different atomic limits. Those are so-called obstructed atomic limits. We can also have systems which do not really have a localized description and are separated by bulk gap closings, but they don't necessarily have boundary states. Those are, for example, fragile phases. And Raquel already introduced us to these concepts very nicely this morning. What I'm going to tell you about is some phases that are going to actually cancel all the other errors as well. So these are so-called boundary obstructed topological phases. These are phases that have topologically protected, globally robust boundary modes. They do not necessarily have atomic descriptions which are symmetric, but they don't necessarily close the bulk gap, so this violates the bulk boundary correspondence. So in order to set the language straight, let's think about a simple bulk obstruction, and that would be just the SSH chain with inversion symmetry. So in this system, inversion you have a single electron per unit cell. And inversion symmetry tells you that that electron may be either in the center of the unit cell or in the edge of the unit cell. And if I were to go for this, the colors don't get a lot of contrast, I'm sorry, but if you were to put that Vanier center somewhere, you need to choose, and these two configurations cannot be smoothly deformed to each other. Either you need to close the bulk gap and mix the degrees of freedom, and then you can jump from here to here, or you actually need to break explicitly inversion symmetry and move the electron charge away from the center. So we can associate, we can say that this one is topological and this one is trivial, or the other way around actually, because for various reasons. One is a simple asymmetry argument. These two phases actually are distinguishable by different symmetry representations. And in fact, actually, Frank already described this very well. And these two, the fact that the electron either sits in the center or in the corner is going to be able to be detectable, but what are the symmetry representations at high symmetry points in the Brillouin zone? But there's also a physical response if we consider that in the center of the unit cell there's a positive ion. Then in the topological case there's a charge displacement between the positive charge and the negative charge, and there's a quantized polarization. We can actually drop translation symmetry from this problem, and we have the same topological distinction. In the topologically trivial case, with open boundaries, we don't have translation symmetry anymore, but we have inversion symmetry. And if I were to put in my electrons in the lattice, I could do that without any symmetry obstruction. And that could be diagnosed simply by seeing whether the inversion center is filled or it's not filled. In the topological case, I would need to choose to put my 5 electrons either to one side or to the other side, which means that I would always have an excess of negative charge in one side and a depletion of the charge in the other, which there would be as well an overall polarization that corresponds to my initial configuration. So there's this very nice correspondence in a bulk obstruction, which is a bulk topological invariant. What is the boundary anomaly? and what is the physical response associated with that. But now, let's look at an example where the bulk actually plays very little role. And that is, the simplest example is the quadrupole insulator. This was a model that interested me a lot because it was just an extension of the SSH chain, also with the quantized physical response. However, there's no clear bulk gap closing transition. This is just an extension to 2 dimensions of an SSH chain. There's also strong bonds and weak bonds. There's a pi flux threaded over every one of these plaquettes. And no matter what we do with these different couplings, the bulk remains gapped, unless there's one point where it actually all closes. So in this model, if we don't have any additional symmetries in the bare model, there's only mirror symmetry in X and mirror symmetry in Y. And that pi flux, what it does is that the mirror in X and mirror in Y anticommute. So this means that the 2 filled electrons in this lattice form a 2-dimensional representation of the symmetry group. And we can see here that this is an atomic limit, so we can just paint the bonds in the unit cell. They can be displaced along these high symmetry lines. We can displace them vertically or horizontally. This is just a basis transformation. In this case, I have my mirror in Y to act like sigma X, and mirror in X act like sigma Z, it's diagonal. And in the other case, I just made a basis transformation to change the basis of change MX for MY. And we can, in fact, adiabatically have complete freedom to move all over these lines. In particular, we can go to high symmetry points. We can put all of these charges in the center of the unit cell. We can shift it to this edge of the unit cell, to the corner, or to the other edge, and we can do that adiabatically. This is the phase diagram of such system with respect to the hoppings, the ratio of the hoppings in the X and the Y direction. These different colors, they just are more like a guide to the eye to tell you whether the electron charge is mostly localized in the position 1A, 1B, 1D, and 1C. However, there's no really gap closing transition between all of these areas. So now what happens if I would actually look instead at a system with a boundary? Let me patch 3 of these different cases. Let me patch it with the electrons in position 1A, electrons in position 1C, and in position 1D. So what we'll see, in all of these cases, we have 18 electrons, space for 18 electrons. We have space for 2 electrons, in this case, right in the middle of each unit cell. Here we have 2 in the middle, 1 at each of the sides. However, if we started by patching it with the electrons in the position 1D, we have a problem. And that problem is the following. I have put a space for 2 electrons, which is shared by 4 corners. So this is exactly a filling anomaly that I have in the SSH chain. However, there's no bulk correspondence. So if I'm going to put here 18 electrons in this model, in this case, and only in this case, I will have to choose if I put my electrons in these corners, on that corners, and in this case, in this type of charge configuration, I will have corner modes, and I will have a quantized electric quadrupole moment. So there's this boundary ambiguity in this problem, which is if I were to cut my unit cell in a different way, I could have singled out, instead of this phase, any other of the other phases. So what do we define by bulk obstruction, by boundary obstruction? Is a bulk phase. This is not something that is a boundary phase, it's a bulk phase. However, what it tells you is that 2 systems which are adiabatically equivalent in the presence of periodic boundary conditions stop being adiabatically equivalent if I put boundaries. And these two different phases, when I do have a boundary, can be distinguished by robust and globally protected boundary modes. So, of course, all the classification schemes we have, they are based on schemes that involve translation symmetry, that involve momentum space. So, in fact, all of these type of obstructions cannot really be captured by non-classification schemes. Instead, they will always need to be captured by something that will break translation symmetry. That can be the surface spectrum, the Vanier spectrum, entanglement spectrum, or something like that. Okay, so now let me be a little bit technical. I don't want to keep it all in this level, and I'll actually tell you how to use the Wannier spectrum in order to capture these phases. So the Wannier spectrum is very instrumental to capture topological phases. What it tells you, basically, is what is the expectation value of the position operator for a specific perpendicular momentum. So, for example, here we have the energy spectrum. There's two field bands. They're degenerate in this case. I fix here my momentum Ky, and I pick up all the states that have that same momentum, and I construct the most possible localized wave function, and that is localized in a position in the unit cell, and that's exactly the eigenvalue of the Wilson loop of the Wilson spectrum. A topological phase that is absolutely topological, let's put it this way, it's topological in an absolute sense, means that I cannot do this localization in all directions. So if I were to change my momentum, I will see that this value will kind of like wind around. It needs to come back to the same place in the unit cell, but the charge is pumped with the actual crystal momentum. A topology, something that has no absolute topology, is in fact something that I would calculate my expectation value of the position operator, and as I change momentum, it kind of like wobbles around one position of the unit cell, which means that I could pick up all my states and find what is the localization of this state. However, so this means that there's no, the technical word is no spectral flow, and it is a system that is Wannier representable. If it's Wannier representable, then I can apply this machinery of symmetry representations, of symmetry indicators, and I can write down what is the band representation that includes all the symmetry eigenvalues for this state in a big matrix, basically. But I can still have something, I can still have some relative topology. With this, I can still tell differences apart. For example, I could tell if two systems have different band representation, that would be different obstructed atomic limits. But we have a little bit of a further point, which is there's actually relative topology within a single band representation. So a band representation of a boundary obstructed topological phase is just a single band representation, Wannier localizable in the symmetry group of your system that corresponds to the point group in the translations. And when I am to calculate the surface spectrum of the Wannier spectrum, I'm going to be always going to decrease the symmetry of my system into a subset. That subset corresponds to lower translation symmetry. I broke translation in the perpendicular direction, and also corresponds to going to the point group, not of the bulk, but exactly at the boundary. So my Wannier bands are described by the bulk band representations of your system restricted to the symmetry group of your edge. And when you do that, you can in fact find different decompositions of your band representations, and those different decompositions can be topologically distinct. And it means that if I were to decompose the band representations, this is the Wannier spectrum with two band representations, with W1 in the bottom or W2 in the top, if I were to invert this, I would need to close the spectrum, the Wannier spectrum. However, to properly define what it means to close the Wannier spectrum, I need to understand what does it mean physically. And I can say it corresponds to the edge spectrum, but then you tell me, okay, but the edge spectrum is something that is unbounded. There's an edge gap, and eventually it connects with all of the bulk states. And the Wannier spectrum, this is a unitary operator, is a periodic operator that just tells you what is the position of your state within the unit cell. So actually, how can I associate a spectrum which is periodic to a spectrum which is not periodic? That is an ambiguity that I'm going to put into the problem, or the ambiguity that is naturally arises in the problem that I need to fix. So in fact, if I have a boundary gap closing, I necessarily have a Wannier gap closing, but the other statement is not true. If I have a Wannier gap closing, I don't necessarily have a boundary gap closing. Let's look at here in this case, we just compare it directly, what is the Wannier spectrum and what is the edge spectrum. We'll see that it corresponds, here when we make this lattice termination, it corresponds to the gap of the Wannier spectrum right at 1/2. So if I were to change my Wannier band representations in that gap, it corresponds to closing the edge gap. However, I can also change the Wannier band representations by closing it around 0, which means nothing but mixing in with the degrees of freedom from the bulk. So what does it mean to have a boundary obstruction? It means that when I fix a boundary, and when I fix the Wannier chemical potential, when I tell you what is the gap that I care about the Wannier spectrum, there is one of these phases of this model that is going to be separated from all the others. So we had these 4 different phases where the electrons were mostly around the middle of the unit cell or the corner of the unit cell. What we did when we put in some boundary is that we decided that the ones that were close to the corner of the unit cell, they will have boundary modes, and they are topologically distinct from all the rest. So it's not that the Wannier gap closings actually matter in this problem. What really matters is the actual boundary gap closing. And if I were to choose a different boundary, I would pick up a different patch of this phase diagram. So the real invariant in this model is actually a Z2 model, a Z2 invariant that tells you have corner modes or you don't have corner modes, rather than what you would expect of a Z2 times Z2 invariant, that if you were to look at all the topology, the full topology of the Wannier spectrum. So this is basically what we had until now. We had the boundaries, the topological boundary states, which are removable. They could be globally robust, which is protected by the bulk symmetry. For example, topological insulators, higher order topological crystalline insulators, and all of that. We can also presumably have some modes which are locally robust, and I could make changes in my system, global changes in my system, to remove them without breaking any symmetry. And now what we have is that we have states which are globally robust. However, they are not protected by the boundary symmetry, but instead from the symmetry at the boundary itself. Okay, so then with this, let me go to a different model, and a model that in this case does not just have boundary charges and not just a filling anomaly, but rather is a model with helical modes, and that's the dimerized weak topological insulator. And the weak topological insulator, we all know how it is. It's just a stack of 2 DTIs. And in this case, let's consider also that there's a C2Z symmetry in the system, and there's a mirror in Z, and they anti-commute. So this is a model that is topological, has strong topology from the bulk, and it's protected by translation symmetry, because it has surface modes which are local, they're separated from each other in momentum space. So one is at gamma and one is at Z. So this is topological, which means that if I were to look at my Wannier spectrum, I would see also spectral flow. This is topological in the strong sense. And if I include the dimerization, by breaking the translation symmetry, I'm going to break that spectral flow. And I will have completely gapped Wannier bands, and in principle, I have no topology left. But I can do that in 2 different ways, and I can do that in 2 different ways that I don't even need to close the bulk gap between one and another. One does not leave any dangling to DTI on the top and the bottom, and the other one does. So this one has hinge modes, and this one does not have hinge modes. However, these hinge modes are not possible to remove except if I close the boundary gap. So these 2 different scenarios are always distinct and are well defined if we have periodic boundaries. It is natural for us to then consider a domain wall between these 2 systems. That would capture the boundary obstruction between these 2. So that's what we do. Let's consider the band representation A and the band representation B. We know that there's no bulk gap closing between the 2 of them. So we know that in fact they are the same band representation. We just chose a different unit cell for both of them. So in fact, this is the band representation A, but shifted. So what we have here, we have a domain wall between our initial dimerized weak TI, and our dimerized weak TI, but just shifted by half of the unit cell. So along this entire plane, I have a mismatch of the unit cell. I can terminate this stacking fault with a screw dislocation. But that screw dislocation is very different from what we normally think about screw dislocations, because the Berger's vector, just as Frank explained to us, it's usually a full lattice translation. So as you go down the screw, usually you come back to the same situation. Here, in fact, you go from A to sublattice B to sublattice A, sublattice B, and that entire plane has a physical presence where sublattice A and sublattice B mismatch. And that is going to be a robust signature of the topological difference between these two. And in fact, is going to be a 2D topological insulator. How much time do we have? 3 minutes. Okay, good. So I can prove to you that this is a 2D-dimensional topological insulator by just removing the dimerization. If I remove the dimerization, I didn't close the bulk gap, and I go back to a problem that we all know, which is the weak TI with the screw dislocation that hosts that helical load that Ran and Ishwarnath found. Can actually make some numerics on this. This is the spectral. It's the energy spectrum painted by where the localization of the wave function is with respect to the center of the screw dislocation. We see that we have a helical mode in the screw dislocation, then there's a bunch of modes filling the gap, which is just the surface states of this model. They go along all around the sample. And if we were to put some dimerization, we would just gap out the surface states as expected and do nothing to the bulk, and that helical mode would remain there. So in fact, this is nothing, that plane there is nothing but a 2-dimensional topological insulator. So now I just want to make a point of that is relevant to look at this type of defects beyond boundary obstructions. In fact, this type of stacking faults can, in principle, pick up lower dimensional topological systems buried inside of materials, and I think it's something that is relevant to now be studied, and some materials have been already showing up, which have interesting spectroscopic signatures coming from such defects, and we still have a lot to do in order to figure out a complete classification and also a way of characterizing them, not really classifying, but how to characterize them from the topology of the bulk. So with that, I get to my overview. I introduced to you what the boundary obstruction is. It's a topology that is intrinsic from the bulk, but it's only revealed given a certain boundary. It violates really bulk boundary correspondence, and for this we need to have some type of generalization of the over-dialectic theorem. And I've introduced to you Vanier band representations, but most importantly to understand what is the topological protection of these phases, I introduced to you what is the Vanier chemical potential that establishes really the relationship between the Vanier spectrum and the edge spectrum. I showed you that two known models are actually boundary obstructed phases, the Bernard-Newt's model, and as well the dimerized weak TI. And I've very briefly introduced to you that it's interesting maybe to start looking at stacking faults in real materials. So that let me thank you for your attention.
Well, we have time for the questions. So